Good morning. What is this room? So,
Good morning, Jose.
Rashika, are you here?
No, I'm Khanh.
Connie. Okay.
Mm.
This is education class 12, right?
Yeah,
Oh, great. Thank you. Thank you for your service. And, the same as yesterday. So, yeah, if I'm not here when the speakers comes in, then you just briefly um, explain him what to do. So he
right,
has to introduce himself before the class and then he can continue.
right.
Okay, thank you. I will be looking around another room. Thank you.
Okay, thank you. Hi, Professor Parisha. Can you hear me?
Hi, yes, I can.
Hi. I'm a volunteer for this section from ES Week.
Hi.
Uh,
Yeah.
and what's happening is, when the time starts, there will be no introduction from ES Week, but
Mhm.
you can just go ahead, introduce yourself, and start the lecture.
Sure. Yeah, sounds good. Hey, Joseph.
Yeah, good morning, Sudhir. How are you?
Good. Good morning. How are you?
Great, great. Yeah, the last day for the education class. So thank
Yeah.
you for your contribution. I just dropped by to say hello and thank you.
Yeah, absolutely. Thanks for organizing all of this.
No,
Yeah, so let's see how many people show up. I hope
yeah,
it shows up.
we didn't have a big audience this
Okay.
time. So I
Mm.
think, they already know that, the video will be available later on YouTube. So
Okay.
many people decided to, join this session asynchronously.
Okay.
So we didn't have a big audience yesterday
Okay.
too. But
All right. That's fine. So I'll just go ahead with the assumption that, it'll be recorded and yeah,
mhm.
not a big deal.
Yeah, and I think you already talked with our volunteer student. His name is
Yes, he
Connie.
just, yeah, okay. He said hi. Yeah.
Yeah, I will be here, but I will be moving around. So if something comes up that student cannot help you with,
Mhm.
then just let me know.
Sure. Sounds good.
Thank you. Good luck.
Sure.
See you
Yeah.
around.
Bye.
Bye.
All right. Good morning, good afternoon, good evening. So let's get started. So I'm going to be talking about optical computing for AI acceleration today. So just a little bit about me. So my name is Sudeep Pasricha. I'm the director of the Embedded High Performance and Intelligent Computing Lab at CSU, also the chair of computer engineering. I have several decades of experience working in industry and with industry, and also more than a decade of experience working with applied machine learning and AI. My research interests are broadly in software algorithms, hardware architectures, and hardware-software co-design for energy-efficient, fault-tolerant, real-time, and secure computing. So in particular, I do quite a bit of work on chip design with emerging post-Moore technologies, also machine learning for embedded mobile wearable platforms, and sustainable high-performance computing. So I think this is something that all of us know, that machine learning is everywhere. So there's a lot of very interesting application domains where we are using machine learning. And so things like self-driving cars, for augmented reality, virtual reality, and many, many other facets of our life today have machine learning algorithms that are running the intelligence behind them. So if you look at the latest trends in AI and machine learning, we can see that there's a lot of excitement around generative AI. So we've all heard of ChatGPT and its clones, but then there's also a lot of interest in the overlap between AI and IoT and augmented intelligence. So in my research lab, we have been applying machine learning to a variety of different application domains. In particular, we've had projects with the Department of Energy where we've looked at designing sensing and perception systems for autonomous vehicles. We've worked on cybersecurity for these vehicles, trying to develop machine learning algorithms that can detect anomalies in vehicle and large-scale networks. We've also looked into applying machine learning for this application domain called indoor navigation with wearable and smart mobile devices. And then we have also looked at trying to improve the energy efficiency of IoT and edge devices with the help of machine learning algorithms that are present in the middleware layer of the device. So when we think about hardware that can efficiently execute machine learning and AI workloads, the challenge that we face today is that general purpose processing is not getting more efficient. We definitely get some gains as we scale technology, but the gains are much, much smaller than the ones that we used to get a few decades ago. So today, our challenge is that for these processors, the power is capped. We cannot increase power above a certain threshold. We want better performance. Unfortunately, that can only be achieved if the energy consumption per operation can be reduced. So we need much, much better energy efficiency. And for machine learning, this is extremely critical. So over the past decade, what has been happening is that we've been looking at specialized domain-specific hardware, not just general-purpose hardware, that can allow us to achieve significant benefits in energy efficiency and also performance. So over the past decade, we've seen some remarkable development in hardware for machine learning. We have seen very interesting architectures. For example, this company called Cerebrus has created this wafer scale processor, where instead of splicing up all the dies on a wafer, they've actually connected them together to create a massive multi-chip system, a supercomputer for accelerating AI. Companies like NVIDIA are introducing tensor cores in their GPUs to speed up AI and machine learning acceleration. And then even companies that normally did not design hardware, for example, Google and Tesla, that was not in the business of chip design, are now essentially creating chips for their products. So there's a lot of excitement around machine learning accelerator platforms. So the landscape today of machine learning accelerators is pretty crowded. If you look at this figure, there's a lot of these accelerators plotted here. On the x-axis, we have peak power. On the y-axis, we have peak performance. The challenge with all of these the platforms is that if we want high performance, if we are in the top right of this chart, then unfortunately our power consumption is also quite high. Conversely, if we want to reduce power, then we end up in the bottom left quadrant of this figure. That means that our performance takes a hit. So what we really want is to be somewhere up in the top left quadrant of this figure. And the challenge is, how do we get there? So it's my conjecture that we need to think out of the box, and we need to go beyond conventional Dennett limited electronic chips if we have a hope of getting to that region of this design space. And that brings me to silicon photonics. So this term actually means a combination of integrated optics and photonic integrated circuits that are implemented on silicon that is CMOS compatible. So essentially, as we will see, all of the devices that are needed for silicon photonics that can help with machine learning acceleration can be fabricated in the same foundries where we fabricate our traditional electronic processors. So today there is growing foundry support, there's open source PDKs, there's a lot of EDA tools, and a lot of very different application areas for photonics that ranges from sensing to biophotonics to augmented reality, light field displays, and so on. But perhaps what most of us know photonics for is its ability to communicate at light speed. So silicon photonics allows us to essentially send data at almost light speed. And that's why in the 80s, we saw this revolution in the telecom domain, where long-haul cables for example, internet and so on, were essentially, they replaced the copper coaxial cables with the much more efficient and high-performance optical cables. In the 1990s and 2000s, we saw the same trend inside a lot of data centers. So in the datacom industry, we saw a lot of these copper cables between racks of computers being replaced by optical interconnects. And then over the last decade and a half or so, we are seeing this integration of optics at an even smaller scale. So we are starting to see optics being integrated at the board level, at the module multi-chiplet level, and slowly also at the chip level. And the reason for that is because optics allows us to decrease the cost of our communication. It has lower power, much, much higher bandwidth than electronic interconnects. So at the chip level, if we take a look at the challenges that we face with data movement, there are significant bottlenecks with moving data. And that's where silicon photonics can make a big impact. So if you think about the energy for accessing a DRAM cell, that takes up about maybe a picojoule per bit. If you're thinking about movement of data between, say, high bandwidth memory stacks, a few millimeters, within the 2.5D chiplet platforms, that's about 10 times higher energy. And then if we think about going off chip and going to, for example, some DDR DRAM, then we're talking about even 10 times higher energy consumption. So optical interconnects can have a big impact on this energy footprint. So they can provide orders of magnitude improvement in energy for moving data from one point to the other at the scale. So at CSU, working with my collaborators, we actually, more than a decade ago, we had been exploring optical interconnects at the chip scale. So this is a test chip that we created in collaboration with Avago. And the interesting thing about this test chip is that it has this optical clock distribution. As you can see, this is like an H tree. And really, this was a proof of concept to understand the challenges with clock signal distribution in the optical domain. The promise, of course, with optical interconnects is that it can allow us to minimize skew and jitter in our clock trees and reduce clock buffering requirements, which have a very heavy cost in terms of energy consumption. So over the last 15 plus years in my lab, we've been trying to look at new ways in which optical interconnects can make an impact in computer systems. So we've been doing quite a bit of research into new network on chip architectures that can combine optical interconnects with electronic interconnects. So we've proposed many different types of architectures, 2D, 3D, free space optics-based architectures. We've been looking at some of the fundamental challenges with these interconnects, particularly relating to crosstalk, where we have interference between multiple wavelengths that creates challenges. We've been looking into challenges related to power consumption. Some of these architectures, because they make use of high-power lasers, can essentially have a very high power consumption. So we have to try to optimize that. And then also temperature is an issue. So we've also done work on characterizing and optimizing for temperature, because a lot of these optical devices are sensitive to temperature variations. Simultaneously, we've also looked at some of the aspects that are just emerging relating to security in these architectures. We've looked at challenges with aging. A lot of times, as we keep using these devices, they degrade in their characteristics, and that leads to some reduction in performance and increase in power. We've characterized, fabricated and characterized many different device level components and then also circuits. And then we've also done quite a bit of work on reliability modeling at the interconnect level. And the underlying thread that connects all of these works is this notion of cross-layer design, where we've essentially attempted to try to make optimizations at multiple layers simultaneously in this design stack that allows us to get much more benefits than if we only focused on one of the layers. So a few years ago, when we were working on this problem of network on chip design with optical interconnects for big data and machine learning type of workloads, this was one of the first times we started thinking about, okay, what can we do to really help machine learning workloads and try to accelerate them with the benefit of silicon photonics. So we came up with these network on chip architectures, homogeneous, heterogeneous architectures, where we showed that some of the heterogeneous architectures, like the one on the top right, are actually a little bit more efficient than homogeneous architectures in terms of energy efficiency. As you can see, the het variant of this architecture is a lot more efficient than the homogeneous version, and it surpasses energy efficiency compared to state-of-the-art at that time. So around that time, we started thinking about, okay, could we do more to help with machine learning acceleration with photonics? So we started thinking about the fact that there are some fundamental bottlenecks with optical interconnects. Photonics is obviously in the analog domain. So there's a lot of reliance on conversion from the digital to analog domain, so electrical to optical conversion, if we want to send anything over an optical waveguide. And then we also need to retrieve the data from optical interconnects. So that means that we need to perform A to D, analog to digital or optical to electrical conversion, which essentially also requires ADC components. And these DAC and ADC components can be quite expensive in terms of their latency, also in terms of their power consumption. So that creates some bottlenecks in the system. But also here's another realization that we had, that typically data from the real world is analog. Whenever we capture data from some sensor, really the output is some analog signal in most cases. And then we then convert it into the digital domain and then work with this data in the digital domain. So the sort of fundamental idea with what we potentially can do to help improve machine learning workload execution is if we could do a little bit more in the analog domain, then we could get rid of this reliance on a lot of DAC ADC components. We still have to use them, but if we could minimize that, and if we could actually do not just communication, but more than communication in this analog domain, perhaps we can get some improvements over what we have seen. And it turns out we can. So if we think about the fundamental operations in neural networks, which are the foundational and perhaps one of the most widely used types of machine learning models, what happens is inevitably at a neuron level, we are doing things like multiplication, summation. Sometimes we do operations like batch norm. We do nonlinear activation, of course, inside a neuron, inside a layer of neurons. And all of these operations, as it turns out, can be performed with integrated photonic components. As we will see, there are various components that can allow us to emulate the behavior of neurons and neural networks. So that brings me to the outline of this education class. So just talked a little bit about some introduction, some motivation. Now, the next thing I will do is talk a little bit about fundamentals of optical computing. Then I'll dive into some cross-layer design of optical computing, look at hardware-software co-design, especially for edge IoT environments, then talk about some open problems and future directions, and then wrap up. So at this time, if there are any questions, I'm happy to take them. I'll pause for a few seconds. All right, so let's go on to talking about the fundamentals of optical computing. All right, so in this slide, I've given a very high-level overview of some of the main components that are involved in silicon photonics or integrated optics, particularly the devices and circuits that matter to enable us to do communication and computation in the optical domain. So the first thing that we need is some sort of a signal source. In the optical domain, of course, that would be a laser. In the electronic domain, of course, it's electrons that move and you apply a potential difference. Here, we need to pump in light through some medium that will carry the information and allow it to be transformed. The medium through which light travels typically is some sort of a confined space, a sort of a waveguide that could have one of these two shapes, either ridge or strip. Then we have some of the more interesting components, the modulators that are very essential for performing either communication or computation. And typically they have circuits that are attached to them that allow them to be adjusted, as we'll see in a moment, and in a manner that can allow them to do the operations that they need to do for communication and computation. Then we have DAC arrays, so digital to analog converters are needed to, in some cases, imprint values onto the optical signal. And then when we are trying to read data from this optical domain, we need some mechanism, and so we need photodetector devices on which the signals can be incident, and then we can convert them into the digital domain if needed, using analog to digital converters. So here's just a snapshot of the fabricated sort of a cross-section view of a lot of these devices. So the reason I'm showing this is just to show that their cross-section and the sort of materials that they make use of, which are silicon, silicon dioxide, germanium, and so on, all of these are compatible with CMOS foundry. So you can actually fabricate most of these devices in a typical CMOS foundry. And again, the fabrication happens in a just sort of a layered deposition-based process, just like for your electronic transistors. We also, beyond these devices, need to couple light onto the chip using some mechanisms like vertical coupling mechanisms or V-groove mechanisms. And on the right, there is this micrograph that I've shown that shows the layout of an optical grating coupler, which couples light from an off-chip laser. So we typically require off-chip lasers. We would like to be able to easily fabricate lasers on a chip. It's not that easy. Of course, there's been quite a bit of work looking into this. There's some success with VCSELs, but most of the time, the more efficient lasers are off-chip, and we just couple that light onto the chip. Now, coming to the component that I said was one of the more interesting ones, the round ring component, the modulator. It's called a microring resonator, and it has some really interesting properties. So each microring resonator, like the ones that I've shown in this example here, couples to a specific wavelength of light, lambda. And by coupling, I mean that it essentially works with a specific wavelength of light. The wavelength that a particular microring resonator works with is a function of three parameters. The first is the radius of this microring resonator, this round ring. Then the temperature around this ring, which can be controlled using a heater element. And then the charge carrier density, which can essentially be changed using a PN junction and some current that's incident there. So here's just a quick overview of how these devices help us. And I'm going to first start with communication. So these devices work as modulators. So what I've shown here is just one microring resonator that I've shown it in red color to indicate that it couples with the red wavelength out of the 4 wavelengths in the waveguide that I've shown here. And suppose we want to send some information in the optical domain. Suppose we want to send this bit stream to some destination optically. So the way that we do it is that the simplest way that we can do it is using something called on-off keying, where if we want to send a 1, we let the red wavelength of light just pass through. If we want to send a 0, then we absorb that wavelength of light. And so this sort of repeats, as you can see for this bit pattern. And then at the destination, what happens is if the wavelength of light is not present, then we detect a 0. If the wavelength, the red wavelength is present, then we detect a 1. And so this microring resonator that you see at the receiver also couples this light out. It drops it on a photodetector. So if there is no light, then really no current will come out of it. And so we can assume that it's a 0. And if there is some light, then we pass this through transimpedance amplifiers, and then we convert it back to the digital domain, but it would be read as a 1. So this is how we essentially communicate in the optical domain. So as you can see, these rings, these microring resonators or MRs, are very important devices that perform modulation, which is another way of talking about the conversion from the electrical to optical domain and from the optical to electrical domain. So a little bit more detail about this infrastructure that's needed. So light that is coming in through this waveguide, the waveguide itself is basically made out of a silicon core and silicon dioxide cladding. And because of principles of total internal reflection, because the refractive index of these two materials is different, we can actually confine light in this silicon core. So what I've shown at the top right is a cross-section of this waveguide for this ring, right? So the ring itself is also a waveguide. And what I've shown is a passive MR. It's a very simple device that's tuned to one wavelength, and that never changes. And this is typically used in some switch architectures, optical switch architectures. You can have 2 different types of waveguides. This ridge waveguide is also used in several scenarios because of some desirable properties that it has. But for doing the things that I showed you, to be able to, for example, modulate and send 0s and 1s, we need to actively tune this MR to a wavelength and get it off resonance or detune this microring resonator so that we can either absorb or not absorb the wavelength. And so for that, we need active MRs that are essentially PN doped or PIN doped. And that can allow us to essentially move this microring resonator into or off resonance to facilitate this sending of information. And as I said, the laser light, we can actually pump in multiple wavelengths, different wavelengths of light simultaneously, and each of them can simultaneously be carrying information in a waveguide. So we can have really high bandwidth because we can have multiple simultaneous carriers in a single waveguide. All right, and this is something that I just mentioned earlier. All right, so coming to machine learning, if you think about what are the basic operations for machine learning, this is just a very simple neural network for an MNIST classification problem. So the fundamental operations in fully connected or dense layers are really just a lot of multiply and accumulate operations. And if you think about the nonlinearity, like any sort of nonlinearity function like sigmoid or tanh or ReLU, again, these also need to be supported. And so these are the two main types of computations. Even if you think about convolution layers, they can be reduced down to matrix multiplications, right? So these are the things that we need to do. And if we are going to use photonics, we need to be able to support these fundamental operations. So here is how we perform these fundamental operations with optical devices. And again, I'm going to look at microring resonators and talk about that. So on the top left, so as I've already mentioned, light can be coupled by these microring resonators. And we can control how specifically we couple light and how much of the light gets coupled. And essentially, that can allow us to potentially imprint some value on this light by using the concept of amplitude modulation. Okay, so we can essentially absorb or couple out a specific amount of light, say 30%, and then we have basically imprinted a parameter 0.7, for instance. And then more generally, on the right, there's this example where we have this little blob that has 3 wavelengths that's moving along. The appropriate wavelength gets coupled with the appropriate microring resonator, and I've shown 3. So if these are 3 activation values that get imprinted, when they hit the second microring resonator bank, and we couple out another fraction of the light, suppose we've coupled out 30%, now we couple out again another 30%. So that's essentially a multiplication between 0.7 and 0.3, right? So that at a very high level is how we can, using amplitude or intensity modulation, imprint actual values and then hope to be able to detect them at the receiver and retrieve those values. We can also do things like coherent summation. So light can actually, in this example at the bottom left, so we can actually have multiple lasers where we have multiple devices as well that are set up in the way that's shown here, where we can actually accomplish summation across different parameters. And that can allow us to also do addition beyond multiplication and support these 2 very fundamental operations in the optical domain. Now, beyond microring resonators, turns out there's a few other types of devices as well. So this is what I'm showing here is a Mach-Zehnder interferometer, and it works on the principles of phase shifting. And so this phase modulation allows us to also imprint certain values on signals of light and be able to perform fundamental operations relating to, for example, multiplications. So here is an example of that at a very high level. A neural network, if you have a sort of a matrix multiplication operation that needs to be done, we can actually decompose matrices into using singular value decomposition into unitary matrices, diagonal matrices, and you can actually implement these using arrays of these Mach-Zehnder interferometers. And that can allow us to essentially perform some of the matrix multiplication operations using these devices. So here's a look at just the sort of layout of both of these 2 very fundamental devices, MZIs and microring resonators on a chip. And so there's a host of different devices that can be used for optical computing. So we have these MR and MZI-based modulators, but then we also have things like couplers, splitters, and so on that are instrumental in allowing us to perform the operations that we need to in the neural networks. So broadly speaking, there are really just two major ways in which today we are looking at performing optical computing. The first approach is coherent computing. The idea here is that we work with a single wavelength of light, and we actually have several devices, typically Mach-Zehnder modulators, MZMs, which is same as Mach-Zehnder interferometers, working as a modulator. And they're essentially arranged in such a way that we can perform multiplication operations. So this relies on phase manipulation, as I mentioned earlier. And in fact, this is the sort of approach that is being taken in several startups that are designing optical computing processors. So as an example, Light Matter is a company that a few years ago released this chip that performs matrix multiplications in the optical domain using Mach-Zehnder interferometer devices. And they showed some promising results in terms of much better bandwidth, much better power efficiency within typically a same area footprint as an electronic processor. However, we've studied these sort of architectures quite carefully. And what we found is that there's a lot of scalability issues. There's a lot of phase encoding noise, phase error accumulation in MZIs, and that makes them not very suitable if we want to think about scaling up these architectures to handle much more complex optical computing scenarios. The second alternative approach to doing optical computing is using non-coherent computing. Here, the idea is that we have multiple wavelengths of light, and we control the amplitude or intensity of the signal and essentially do the sort of operations like I showed you in the animations a few slides ago to perform addition and multiplication and other types of operations. So the advantage of this approach is that it has a lot more parallelism. We're working with multiple wavelengths simultaneously, unlike in the previous approach where it's just one wavelength. And then, so we can have, for example, 32 or 64 wavelengths simultaneously being transmitted and operated on in just one waveguide. This sort of an approach is also a lot more scalable. Each operation can be performed in a very compact way. These microring resonators are much smaller than the Mach-Zehnder interferometers that coherent computing makes use of. So there's a lot of desirable properties for this type of computation engine. But there are still a lot of challenges, and this is, again, an emerging area. And so non-coherent optical computing, we need to solve a lot of problems today. And I'll highlight a few. One of the major challenges is resonance shifts, undesirable resonance shifts for these microring resonators because of fabrication process variations or thermal variations. So essentially what happens is that, as I mentioned earlier, each microring resonator is tuned to a particular wavelength, but because of the ways that we fabricate devices, because of imperfections in these devices, it may be the case that a microring resonator is not exactly coupled to a particular wavelength anymore. Or if the temperature changes, that also causes the microring resonator to go off resonance, and it cannot couple with that specific wavelength of light that it's supposed to. And so that, you can imagine, can lead to a lot of errors when we are using these devices if they're not working properly with the wavelength that they're supposed to. The other challenge that we have to worry about is crosstalk. So each of these devices, these microring resonators, are not perfect. And so even if a particular microring resonator is working with a specific wavelength, for example, in this case with the green wavelength, it may still couple out signals from other wavelengths because these devices are not perfect. And that can cause some errors, especially if you have a lot of modulators along a waveguide that are coupling light of different wavelengths. So compensating for this can be done, but it consumes a lot of power as well. So we have to come up with better mechanisms to deal with this. And then lastly, anytime a signal propagates through an optical signal, a laser signal propagates through this silicon core waveguide, or any sort of material, it incurs losses. And that's because we are not sending the light through vacuum or free space. It's actually going through material where some of the photons do get absorbed. And so we have these losses. To compensate for that, we have to increase the laser power, which again is an overhead. So I'm going to very briefly talk about these three challenges because they're very important. They motivate the sort of solutions that we need to come up with. So here I've shown, again, just a single microring resonator that is resonant with this green wavelength, works with this green wavelength. What may happen is you can have process variations because of fabrication imperfections that can cause the resonant wavelength of this microring resonator to not be green anymore. Suppose it's a slightly different wavelength, like maybe yellow, okay? And so we can make use of tuning circuits to actually bias this microring resonator, change the charge carrier density, and bring the resonance or the microring resonator back in resonance. We can also make use of microheaters to do the same thing, to increase the temperature, and that allows us to, again, bring the microring resonator back to resonance. So this is how we can compensate for these variations, which are inevitable whenever we execute anything on any compute platform. But unfortunately, these sort of techniques have a cost associated with them. They have a power, they have a latency associated with them, and that reduces energy efficiency. So again, coming to these tuning circuits, really there's two approaches that we can use for compensating, as I mentioned briefly in the previous slide, two ways to compensate for these variations. One is thermo-optic, the other is electro-optic. So the thermo-optic approach that uses these heating elements, the nice thing about it is it can compensate for large variations. Unfortunately, its latencies are very high. So we're talking about microsecond latencies. So that is quite slow. And then we have electro-optic tuning, which essentially uses carrier injection. That is much, much faster. However, the tuning range that it can support is very small. So it can only adjust for very small variations. The second challenge that we have is crosstalk, as I mentioned. So these microring resonator devices are not perfect. And that means that whenever they're designed to couple with a particular wavelength, they might couple a signal from another wavelength. And that creates crosstalk noise. It's typically called heterodyne noise when it happens across multiple wavelengths. You can actually surprisingly also have crosstalk within the same wavelength. So it's called homodyne crosstalk. And both of these scenarios create crosstalk noise. And what that ends up doing is it creates errors in the bit streams. It might flip a 1 to a 0 or a 0 to a 1. And that ends up being not good. It ends up decreasing our signal to noise ratio. It increases our bit error. Both of these things are not desirable. So crosstalk noise needs to be addressed as well whenever we design these sort of systems. And then lastly, as I mentioned, when light is traversing these media, these silicon media, then actually it incurs losses, and there are different types of losses. So anytime you couple light, there is coupling loss. If you just pass by some modulators, maybe some of the light gets partially absorbed by them, and that's called through loss. Whenever you have to traverse a long distance, and there is propagation loss. Anytime your waveguides bend, there is bending loss. And so typically there is a lot of sources of losses. And what ends up happening is we need to ensure that the signal has sufficient power so that it can actually be detected. We don't want the signal to completely die out before it gets to the detector. So what we need to do to compensate for these losses is to increase laser power. And of course, laser power can be quite substantial. So this is another challenge that we need to overcome in non-coherent optical computing systems. All right, so that's some fundamentals of the devices and challenges relating to optical computing. I'd be happy to take any questions if there are any, and I'll pause for a few seconds. All right, so let's resume. So next, what I want to talk about is let's take a look at some potential architectures that can help us perform optical computing. So in my research lab over the past several years, what we've been doing is developing this family of optical computing-based machine learning accelerators. We've designed accelerators in the optical domain for CNNs and DNNs, for RNNs, for transformers, and also for graph neural networks. So I'm going to talk a little bit about each of these different types of models and their unique requirements from a computation perspective, and what we can do with optical computing. So I want to start with perhaps the most widely used set of models. These are convolutional neural networks, CNNs, and DNNs, deep neural networks. In my lab, we've used these models extensively in some of the research that we are doing in the automotive domain for perception in self-driving autonomous vehicles. We've developed new types of architectures, also optimized these architectures for deployment on embedded and IoT type of platforms. So a few years ago at DAC 21, we proposed this cross-light optical computing accelerator for CNNs and DNNs. This is an architecture that's called cross-light because it is cross-layer optimized. We perform optimizations at the device level, at the circuit level, and at the architecture and OS level. And I'll talk very briefly about some of these in the next few slides. And so this allows us, and in fact, this is one of the first cross-layer optimized optical computing accelerators that heavily relies on these microring resonator devices that I talked about. So just to give you an example of some of the things we did at the device level to perform optimization to make these devices more suitable for our optical computing requirements. On the right in this slide, you can see a microring resonator device. It has a certain width for the actual loop, the actual ring. And then there's the input waveguide that also has a certain width. Now, on the figure on the left, what I'm showing here is on the y-axis, we have the resonant wavelength shift slope. This is essentially a way to understand this is essentially it's the susceptibility to process variations and errors due to that. So if this is low, that's a good thing. And so on the x-axis, we have the waveguide width. So in this case, we're looking at both the waveguide widths of the microring resonator and the input waveguide. Both of the widths are the same. And so if you look at the green curve, the thickness of these waveguides doesn't really make that much of an impact, but the width of these waveguides, if we keep increasing it as we go from left to right, it reduces the resonant wavelength shift slope, which essentially means that these devices are less susceptible to fabrication variations, which is a good thing. Unfortunately, this reduction in susceptibility to variations comes with a reduction in crossover coupling as well, which is actually very unfortunate because we need a higher crossover coupling if we want these devices to work correctly. So what we did was we explored many different types of these devices, and we came up with this very interesting microring resonator device structure where the width of this loop waveguide is different from the width of the input waveguide. And we essentially found that if you look at the figure now, that as we increase this width, we can actually reduce the susceptibility to variations, but it does not dramatically reduce our crossover coupling by as much as in the previous case. In fact, we can find a sweet spot, a width where we have an acceptable crossover coupling, but we also have some a reduction in susceptibility to process variation. So that's something that was very interesting, and that's the sort of devices that we need for our accelerator. We collaborated with CLAT and fabricated these devices to validate our conclusions. So coming to the circuit level, so if you recall, we just talked about these tuning circuits that are meant for making these MR modulators go in and out of resonance. And we absolutely need these tuning circuits in a computing substrate in the optical domain to imprint parameters accurately. So the challenge, of course, is that so I'll talk about challenges in a second, but this is just showing that in a bank of these microring resonator devices, these tuning circuits are very critical, and they modulate the signal. And here I've just shown sort of intensity modulation. The actual intensity modulation depends on the parameter value, the weight or the activation that gets imprinted on each wavelength. So in our cross-slide architecture, we came up with a new hybrid electro-optic and thermo-optic tuning approach. The idea is that we want to rely on electro-optic tuning as much as possible. So, and that's because it's much, much faster than thermo-optic tuning. And then periodically, we would rely on thermo-optic tuning if needed to perform a much larger shift across the entire bank of microring resonators. And we essentially integrated this interesting technique called thermal eigenmode decomposition that allows us to collectively tune all microring resonators in a bank while canceling thermal crosstalk. So the heaters that are present that do thermal optic tuning can also cause resonance deviations in the microring resonators in their vicinity. So that's the thermal crosstalk that we explored and minimized. In order to do that, we explored optimal layouts and optimal dimensions of these microring resonator devices, and we came up with some recommended distances at which we wanted to fabricate these components. At the architecture level, so the highlighted box here indicates our high throughput engine in the optical domain to perform multiply and accumulate operations. Of course, in this case, we also, in most cases, we have parameters and activations stored in the digital domain in some memory. Unfortunately, we don't have good ways of storing information in the light domain, so we have to still use electronic memories. But we can make use of these digital analog converters and ADCs to perform the conversions back and forth. Of course, we want to minimize the reliance on them, which is what we do in our architecture. And then some of the other operations and storing information happens in the electronic domain, but all of the main the compute-intensive, time-consuming operations actually happen in the optical substrate. So in our architecture, we decided to have a separate part of our architecture for accelerating convolution layers and another part for accelerating our fully connected or dense layers. As you can see, in each of these engines, we have VDP units. These are vector dot product units. And so the number of the VDP units and also the number of these microring resonator arms inside each of these units is something that is a very important architectural design parameter. One thing to note is that for convolution operations, the number of, or actually the dimensions of the dot product are much, much smaller than for fully connected layers. And so in that case, in the same area, we can fit in a lot more VDP units than for the fully connected layer. So the structure of the VDP units is actually a bit different across these two engines. So we explored that, and then we also came up with optimizations to reduce the laser power for each of these VDP units. So here's a look at some experimental analyses. So we looked at 4 different models, which have parameter counts that range from 60,000 all the way up to around 39 million. They have different numbers of convolution and fully connected layers. And we did our analyses in terms of what happens when we make use of lower bit width parameters and activations. And that's because in the analog domain, we have to reduce the precision a bit because higher precision is very difficult to support. So 32-bit precision is very difficult, but we certainly can support things like 8-bit resolution. So if you can look at the validation accuracy for these 4 models, and on the x-axis, I've shown the number of bits for your weight parameters. You can see that we don't really necessarily need to go quite beyond maybe even 8 bits. We can even get by with fewer than 8 bits if needed, but anywhere from 8 to 16 bits is fine. And so that's sufficient resolution, provides us with sufficient accuracy, and allows these models to be accelerated in the optical domain. We performed quite a bit of optimization at the architecture level to determine the number of VDP units across the 2 engines that we had, and the actual architecture of each of those VDP units. So this figure is really just showing on the y-axis frames per second, just the throughput of these models. On the x-axis, I've shown energy per bit for these models, and then the color shows the area of the entire accelerator for a particular configuration. And the configuration that I've shown highlighted in the figure is the optimal one. It's the one that has the best ratio of frames per second to EPB, basically one that has high performance and low energy consumption. So we compared with many different accelerators. So here's a look at a few accelerators that had been proposed by that time that performed accelerations of CNN and DNN models in the optical domain, using different types of devices as well. For example, the second approach, Holy Light, makes use of micro disks, which are a little bit different than micro ring devices. And then we also compared against general purpose CPUs, GPUs, and dedicated accelerators in the electronic domain. So here's a look at some results. So these are power results. So from a power perspective, we estimated that Crosslight would consume about 75 watts of power, which is not the lowest. Out of all the accelerators, there's many accelerators that can consume much, much less power than our accelerator. So we really don't win out in terms of power consumption. However, when we look at energy per bit, this is just a comparison across the 4 different machine learning deep neural network and CNN models across 4 different variants of Crosslight. Cross-Opt-TED is the one that has all the optimization. The baseline one does not. The TED one just has the thermal eigenmode decomposition optimization. Cross-Opt is just has the device level, microring level optimization. And then so combining all these optimizations allows us to get the best results. And so we can actually, and then compared to the other 2 optical accelerators, we can get about 9.5x lower energy per bit, which is a very promising result. Then if we compare against all the accelerators, not just the optical ones, if we compare against the electronic ones as well, from an energy per bit perspective, there is a significant reduction with Crosslight, the best Crosslight configuration compared to the other architectures. And then also in terms of throughput power efficiency, kilo frames per second per watt, we have the highest throughput power efficiency in Crosslight. So these results show the promise of doing machine learning acceleration in the optical domain. So next, I want to talk about another type of model, recurrent neural networks. And when I talk about RNNs, I'm also talking about models that make use of long short-term memory and gated recurrent units. These are all models that are designed for sequence learning a sequence of data, maybe information about stock prices over time, or any sort of maybe network information over time, or words in a sentence that are fed into these models in a sequence. So these models are good at learning sequences and the relationship between elements in a sequence. In our lab, we've been using these sort of models for anomaly detection in cyber-physical systems, in automotive networks, and we found that there's some really interesting things we can do with these machine learning models. So we were interested in saying, could we perform optical domain acceleration on these type of models? Now, the thing here that we need to know about here is that these sort of models have fundamental units like the 3 that I've shown here, the plain vanilla RNN cell, or a GRU cell, or an LSTM cell, that have structures that are a little bit unique, different from your DNNs and CNNs. For example, there's a heavy reliance on sigmoid and tanh nonlinearity, and then several places where there's multiplications and additions. So when we create an accelerator for these sort of models, we need to be able to accelerate these fundamental cells efficiently. So we came up with this architecture called RecLight for recurrent neural network acceleration. I've shown just at a very high level a schematic of that. We presented this work at ISVLSI last year. And here is sort of a zoomed in view of the multiply accumulate array. Again, it has vector dot product units. We call them VDUs in this case. Pixels are just your laser signals. And so the thing that we did here was we made some changes. We created these vector dot product units and we integrated memristor cells to store certain values and improve the energy efficiency of these sort of architectures. So we can write, for example, a weight parameter to these memristor cells, and that can allow very stable modulation over a lengthy period of time, assuming some sort of a weight stationary policy. And so this sort of helps with our efficiency. And also for all of the nonlinearity using sigmoid and tanh, we came up with this approach of using semiconductor on-chip amplifiers that could allow us to emulate either a sigmoid or a tanh nonlinearity. So just at a very high level, a quick look at some results. So by the way, this was the first optical domain accelerator for recurrent neural networks. So there's no other optical accelerator we could compare with. However, there were some accelerators in the electronic domain for LSTM models, for GRU models. And then we looked at a comparison with these. And we looked at 3 different data sets. And we created 3 different RNN type models, just a plain vanilla RNN based model, then a GRU based model, and then an LSTM based model to learn the patterns in these 3 data sets. Here's a look at the results. So for giga operations per second throughput, you can see that RecLight for when we are comparing against the LSTM accelerators is quite promising. And then if we look at energy per bit as well, and we're looking at GRU accelerators here, that's also quite promising. And here we're looking at the LSTM accelerator. So you can see that RecLight has much smaller energy per bit in most cases. In this first case, maybe not as much, but in most cases, it has much lower energy per bit or better energy efficiency. So we can actually get up to 1730x and 2632x improvement in energy per bit and giga operations per second compared to state-of-the-art electronic RNN accelerator. So this is a very promising result. I'm going to pause for a moment here. Any questions? All right, so let's continue. The next type of model I want to talk about is transformers. So this is the model that's at the heart of ChatGPT and a lot of large language models that are heavily being used today. These sort of models are very interesting. They're not just used in large language models and applications like ChatGPT. For example, we made use of a vision transformer in mobile and IoT devices for our indoor localization and navigation project in our lab, where you can see that the goal here is to really just create a real-time way to help someone navigate in indoor spaces using a smart device, just like we do with GPS outdoors. But a GPS doesn't work inside buildings and underground structures. So we actually showed how we can optimize a vision transformer and deploy it on a smartphone. So we were interested in trying to see how could we accelerate these emerging transformer neural networks in the optical domain. And so fundamentally, these transformers have an encoder structure and a decoder structure. If we just sort of zoom in into the fundamental units, there is this multi-headed attention that requires the generation of the query, key, and value, which involves matrix multiplications. And then the outputs of these and these keys are actually fed into, after some linear transformations, into a scaled dot product attention engine that again requires several sequence of matrix multiplication masking, scaling, nonlinearities as well. And then the feed-forward unit shown in blue essentially also requires nonlinearity, multiplications, summations, and so on. So this is actually a very complex component. And typically in transformers, we repeat these fundamental components and stack them together. And these models can be very, very complex. So it's a little bit more challenging to accelerate these transformers. So earlier this year at GLSPLSI, we proposed the first optical domain transformer accelerator called TRON. I'm going to just give you a very high-level overview of that accelerator. So this is, again, looking at a high-level architectural view. At the bottom square is essentially our optical computing engine. And at the top, we have our electronic control units that are essentially orchestrating a lot of the operations in the optical engine. So here's a look at the multi-headed attention unit. So here we essentially need to perform matrix multiplications in the attention heads and also softmax. A naive way to try to do these operations is to, because it's not as straightforward as in other models, so you could try to generate the key after the multiplication, convert it into the digital domain, you can buffer values, then you generate a transform, then you convert the matrix back to the optical domain. And so these are not that efficient in terms of the time and the energy required. So we came up with some more elegant and efficient ways to perform matrix multiplication decomposition. And I'm not going to go into that, but details are in the paper. That allowed us to do a lot more of the operations in the optical domain, including transpose and so on. And then for softmax, what we did was we approximated this nonlinearity using simple digital circuits and also lookup tables to perform sort of approximate exponential and logarithmic operations. So the multi-headed attention unit has these attention head accelerators. It also has these linear layers. And again, it's really just an extension of what I showed you for the other architectures. We have these arms of microring resonators where we imprint activations to multiply them with weights. And then you see a positive and negative waveguide. These are for essentially accumulating the positive values and negative values that allows us to then get more accurate results. And the BPD stands for a balanced photodetector that can essentially sum these things, the currents together to create an appropriate output after the multiplication. So basically accumulating things. In terms of the normalization, so we can also do some of these operations in the optical domain. So we made use of certain special types of microring resonators to be able to perform normalization. In terms of the feed-forward layer, so here again, we have these microring resonator banks to perform matrix multiplication for adding biasing. And then in these blocks, we also need to support some unique nonlinearities, for example, GELU. And so here we made use of a SOA, semiconductor on-chip amplifier-based sigmoid structure, together with a couple of other components to emulate this sort of a GELU approximation. So from a microring resonator design optimization perspective, our goal was to reduce heterodyne crosstalk. We want to have the highest tuning range and the highest signal-to-noise ratio. So we explored many aspects at the device level. So again, for each of these accelerators, we're doing sort of a cross-layer design. So we explored this MR design space. Here, we're looking at tunable range, Q factor, which is the selectivity of the microring resonators, signal-to-noise ratio, which we want to increase as much as possible, and also channel spacing, which is essentially spacing between the different waveguide groups that we have. So we were able to find through very detailed device level exploration optimal configurations for these that would work for our transformer acceleration needs. And we were able to fabricate devices, validate that indeed the properties that we care about were preserved in these devices. At the architecture level, again, we also performed a lot of exploration. Our goal is to achieve the lowest EPB by GOPS or the highest GOPS per EPB. And we explored different aspects of how many accelerator engines for the multi-headed attention do we need, how many layers should we support simultaneously, how many rows should we have in the MR arrays, how many columns, and so on. And the figure really shows sort of different design points and their power, their throughput, and their energy per bit, and also their area. So the star, the pink star, essentially shows the configuration that we ultimately chose, which had the lowest ratio for EPB to GOPS. So here's a look at some results. So on the left, by the way, we're looking at 4 different types of transformer models. As you should see here, there's a different number of parameters in each of these models. And so we're looking at, in this figure, power and latency. And really what I've shown here is just the contribution of different subcomponents to the power and latency. So you can see for power, the attention heads consume the most amount of power, followed by the fully connected feed-forward units and then the linear units. From a latency perspective, however, we can see that trends are slightly different. Attention heads do take up quite a significant chunk of the latency, but then the normalization and addition also add some latency in addition to some latencies from the other components as well. In terms of comparison, so we compared against many different electronic accelerators for transformers, FPGA-based accelerators, resistive RAM-based or processing and memory-based transformer accelerators, and then also a GPU, a CPU, and also a tensor processing unit from Google. And you can see from a perspective of giga operations per second, our Tron architecture has one of the highest GOPS. We get at least up to 40 or at least 14x improvement, if not more. And then looking at energy per bit as well, Tron is a much superior solution. We get at least an 8x improvement in latency. So these are, again, very promising results for optical computing for these advanced models that we are seeing today. The last application and type of model that I want to focus on is graph neural networks. So graph data is actually very, very interesting. It's quite complex. As an example of a graph data set, so this is a social network data set, Snap, Ego, Facebook, where the graph is made out of social connections between users. And our goal is to predict user interests and recommendations that, for example, this is something that Meta or Facebook does when they create your curated feed that you see every time you log into Facebook. And then also in other domains like bioinformatics, we have these representations of chemical compounds as graphs. And what we're interested in is predicting the compound properties of these sort of structures. So again, that requires some graph data processing. So the challenge with graph data is that these sort of structures can be pretty irregular and complex. And so trying to accelerate them is not that straightforward. So in the past, the sort of predominant approach that was used was these graph kernel methods. So essentially, these sort of methods were essentially applied machine learning principles using kernel transformations to map graph data into feature spaces. And essentially, it allowed us to measure similarity between pairs of graphs, but the mapping function is actually deterministic rather than something that can be learned. So if you created this for one problem, you could not easily take this to another problem. You would have to sort of start from scratch for a new problem. And then there's also a lot of computational inefficiencies in pairwise similarity computations with these graph kernel methods. So graph neural networks that were first, sort of the first successful application came about in around 2016 with graph convolutional networks, allowed us to use deep learning for graph data. And it turns out that these sort of deep learning models were quite efficient, and these sort of models are actually quite heavily used in a lot of different application domains. And so these models are now sort of the more de facto graph processing engines. And if we want to accelerate graph data processing, we need to be able to accelerate these graph neural networks. So here's just at a very high level what a graph neural network consists of. There's really 3 main stages. The input graph, which has some nodes. There are some features associated with these that can be represented using vectors. And then there is edges or connections that give you some information about the relationship between the nodes. Then we need to perform aggregation in a GNN, which involves summation, mean, max, min type of operations. And then we also need to perform a combine operation that essentially leads to linear transformation operations or nonlinear activation function-based operations. All right, so the challenges with accelerating these graph neural networks is that graphs have a lot of graphs have irregular structures, and so this irregularity creates a lot of complexity if you want to efficiently execute graphs. If a node has a connection to 1,000 other nodes versus a node having a connection to only 5 different nodes, it leads to a lot of heterogeneity in our compute requirements. There's also a lot of sparsity in several different graphs. There's usually a very high requirement for data accesses, also irregular accesses from memory. And then there's many different types of graph neural networks. So there's graph attention networks, graph convolutional networks, and so on. And these require slightly different ways of acceleration of these models. So we need to come up with a flexible engine that can allow us to accelerate different types of graph neural networks efficiently. So recently, we proposed this accelerator called GHOST, that is a graph neural network accelerator using silicon photonics or optical domain computing. In fact, my student Salma will present this work on Monday, in a few days from now, at ES Week, at the Cases conference. But I'll just give a very high-level overview here. So what I'm showing here is some of the basic building blocks of this accelerator. And really, fundamentally, there are these 3 main blocks to perform aggregation, combination, and update. And then we have these, so we have actually V processing lanes. So each lane processes 1 node at a time. And then we have N edge control units. Each of them, they each fetch a neighbor node and a corresponding edge data and forward it to the gather nodes. So this is essentially at a very high level some of the components that we needed to design to accelerate graph neural networks. Sort of diving a little bit deeper into some of these components. So the reduce block makes use of an optical coherent summation block because the summation is essential. Each row is assigned a feature. Each column is assigned a neighbor vertex. And we are able to, through this block, support various aggregate functions across GNN models like summation, mean, max, and so on. And then all optical signals are combined and passed to the transformer units, or they're buffered in some cases. So in this transform unit, we have essentially microring resonator bank arrays to perform linear transformation. We have made use of broadband microring resonators to perform operations that approximate batch norms. Then we have these activate units that perform nonlinear activation. So we can use, again, these semiconductor on-chip amplifier-based components to emulate nonlinearities like ReLU or sigmoid or tanh and so on. And then for softmax, which is a little bit more involved and challenging, we make use of lookup table-based operations. So we performed several optimizations for orchestration and scheduling computations on this substrate. Also several device and circuit optimizations. Some of these I've talked about, at least at the device level I talked about earlier, so I'm not going to spend too much time there. But I'll briefly mention a few of these. I cannot mention and describe all of these, but all the details are in the paper. So the first thing that I want to mention is just the pipelining and scheduling. So GHOST, essentially the accelerator adapts according to the model requirements. So the graph attention networks, for example, require a different way of orchestrating the operations versus, for example, graph convolutional networks. So we accommodate that, and we can overlap the computation operations in a way that allows us to improve throughput across different model types. Then we also perform this weight DAC sharing. So we can actually share one set of digital to analog converters across all transformer units. And that allows us to reduce the number of DACs, that allows us to reduce their overhead. And particularly it allows us to reduce energy overhead. However, this optimization does have some requirement in terms of being able to synchronize with the different processing lanes. So it has to be done a little carefully. Then at the device level, again, we're making use of microring resonators. So we performed a design space exploration there for our unique requirements for these type of computations. So the figure here shows just an analysis between signal to noise ratio, the wavelengths, the number of rings, and the signal to noise ratio cutoff is shown in this sort of a red plane that I've shown here in a 2D plot. So essentially, we wanted to get a microring resonator with desirable properties, which after exploration we were able to, that allowed us to reduce both heterodyne and homodyne crosstalk in our system. So here's a look at some results. So this is really only looking at across 4 different graph neural networks, GCN, GS, GAT, and GIN, and across 4 different data sets that these models were trained on. And then the last set of bars just shows an average set of results. And then each of these bars represents a different combination of optimization. So the baseline is just our architecture without any of these optimizations. Then we combine different optimizations, buffering and partitioning, pipelining, a combination of that, then a sort of write back or DAC sharing. And results are all normalized to the baseline model, and we're looking at energy. And so what you can see here is that a particular combination, certain combinations did quite well. So for example, this buffering and partitioning together with pipelining and write back optimization, all working together, led to some good results. Perhaps the best results came with this particular combination of buffering and partitioning, of pipelining, and DAC sharing. So significant reduction in energy if you use these 3 optimizations together. And so that's what we did in our final architecture design. We considered these 3 optimizations. And we had to sort of actually not use a few optimizations because they sort of negatively impacted other parts of our system. So now here's a look at comparing our accelerator with other types of platforms. So this is, again, looking at GPUs and CPUs and TPUs, along with several accelerators in the electronic domain. Again, there is no accelerator in the optical domain for graph neural networks. Ours is the first optical domain graph neural network accelerator. And so we couldn't compare against any optical platform. But we compared against those electronic platforms. We looked at the data that they reported. And then for GPUs and CPUs, we actually ran our own models, also TPUs, on the real platforms, the hardware platforms. And so the giga operations per second is what we're looking at. So here you can see that Ghost is able to get at least a 10.2x improvement in giga operations per second across these platforms, which is a very promising result. Here's a look at the energy per bit results. So here again, we can see that across all of these different graph neural networks, across all the 4 data sets for each of them that we ran them for, and across all platforms, Ghost, our accelerator, is able to get at least a 3.8x improvement in energy per bit compared to these platforms, which again is a very promising result. All right, so that was just an overview of some of the cross-layer designed and optimized accelerators in the optical domain for different types of machine learning models and use cases. I'm going to pause for a few seconds here. If there are any questions, I'll be happy to answer them. All right, so let's continue. So we're almost towards the end of this education class. So let's wrap up. So the next thing I want to talk about is hardware software co-design for these sort of optical computing based accelerators, particularly target towards edge IoT environments. So today it's actually nothing surprising that there's a lot of reliance on connected smart devices. Today we have seen this massive exponential growth over the last decade plus in terms of the adoption of embedded and IoT devices. And in fact, today embedded computing is the dominant form of computing, and it's increasingly being used to run machine learning applications. It's a nice sort of side benefit with these billions and billions of devices that we have. We can actually get the massive amount of data that we need to train some of our very complex machine learning models. So there's a nice ecosystem that has emerged today with these devices and them generating data that can train better and better machine learning models. Now, the fundamental challenge, however, with these devices is that they are very resource constrained. So a lot of these edge devices or IoT or mobile devices generally have a very small power envelope. And then they also have much fewer compute resources, much smaller memory, many challenges. But the challenge that really matters for designers of these accelerators that could go into these systems is fundamentally the power challenge. So our computing budget for a lot of these devices cannot exceed 10 watts. In fact, in many cases, it has to be even less than 1 watt for small battery-driven devices. And so earlier I showed you how our cross-light architecture consumes about 75 watts of power. That will just not work for these sort of use cases if you want to use those accelerators within IoT embedded devices. So if we want to design these sort of optical domain accelerators, we need to do things a bit differently. And so over the last few years, we've been coming up with these new types of architectures in the optical domain that target edge and IoT platforms. So we've designed these binary quantized, heterogeneously quantized, sparse optimized, and sparse coherent optimized accelerators. I'm going to talk very briefly about a few of these, and just to show you what are some of the things that we did differently in those accelerators to adapt to the edge and IoT use case. So the first thing that I want to talk about and the first accelerator is actually the Robin accelerator that we proposed a few years ago and was presented at ES Week. And this is an accelerator that supports the acceleration of binary models. So now this is a very interesting sort of a model where if you have neural networks that have weights that can only be require just 1 bit, typically the parameters require 32 bits, but instead of that, if you just use 1-bit weights, it turns out that we can get away with that. And as long as we don't use 1-bit activations, which would be a big penalty. So this plot here shows for 4 CNN models, accuracy on the y-axis, the number of activation or input bits, and we're using binary weights, so just 1-bit weights. And what we found in our analyses, and what many others have also found, is that we can actually get away with using maybe a much smaller number of bits for both the activations and the weights. So for weights, here we're using 1 bit. The red line essentially shows that if you have 4 bits for your activations, that also provides pretty good accuracy across these specific applications. So in our Robin architecture, we can actually try, and we actually did accelerate these sort of models that had much fewer bits than our baseline models that all make use of 32-bit activations and weights. And by accelerating these sort of models that are much more compact in terms of the parameter sizes, we can actually have much smaller memory requirements, much better latency, much lower power overhead. So these are all things that matter for edge and IoT contexts. So we created this Robin accelerator, which essentially improved upon and changed the cross-light architecture so that we could support these smaller bit widths based on our analyses. We also added some new features, the photonic batch norm implementation, We created a completely new data flow pipeline. We also, again, made optimizations at the device, at the circuit, and also at the architecture level for this Robin accelerator, just like I've shown for the other accelerators. Here's a look at the architecture level exploration. Each of these points in this 3D space represents a specific configuration. There are two specific configurations that I've highlighted here. EO is the most energy optimal, that essentially has the highest frames per second per watt. And then the performance optimal is the one that has the best frames per second, essentially just optimized for performance without significant concerns about energy. And so, and then we're looking at area, FPS, and energy per bit. So here's a look at some results. So now we're looking just at power. We compared against several electronic domain, also photonic domain accelerators for CNNs and DNNs. And here's the last two bars are the Robin architecture. EO is the energy optimal configuration. PO is the performance optimal. So you can see that this energy optimal configuration actually is much more energy efficient than our cross-slide architecture. We got about a 10x reduction in power for this particular configuration. So this is exactly the right direction. This is exactly how we want to design optical accelerators for the edge and IoT context. Here's a look at energy per bit. Again, from an energy per bit, we're actually superior to all the other accelerators, specifically these electronic and then photonic accelerators. So this is, again, very promising result. Then we also looked into supporting models that have heterogeneous quantization. So we designed this architecture called HQNNA, where if you look at the table, we're looking at 3 different models, AlexNet, ResNet20, and this SVHN-based CNN. And if you look at the model that, or the row along with HQNNA in each of these 3 parts of the table, you can see that the bit widths are represented using this array of different values, 6, 6, 4, 4, 4. So we actually performed a layer-wise quantization. We found the optimal combination of number of bits that are needed. Some layers need more bits to preserve accuracy that we care about. In other layers, we can actually get away with using much fewer bits. And so that's the idea behind heterogeneous quantization. And then after creating these sort of models, we created the hardware to be able to adapt to this heterogeneous quantization. So just like with Robin, here as well, there is a close synergy between the software optimizations and the hardware optimizations that we did. So that's why I talk about it in the context of hardware-software co-design. And you can see here that in the bottom, I've shown the energy per bit results. So here across the models, across different optical accelerators, I've also shown Crosslight and Robin. HQNNA can actually lead to much lower energy per bit. And this is the work that we presented last year at GLS-LSI. Another way that we can potentially make our models more amenable to edge IoT environments is to optimize them by optimizing for sparsity. Now, in a lot of these neural networks, when we work with activation functions like ReLU, you know that if a value is negative and passed through ReLU, it's going to become 0, right? So there is some inherent sparsity or 0 values in the model outputs, but then we can also make use of techniques like L1, L2 regularization during training to induce parameter sparsity. In other words, we want to penalize weights that have high magnitudes, and we want to encourage the design of a neural network that has small or close to 0 or even 0 weights as much as possible. And so the nice thing here is that anytime we have a 0, the operation can be done very efficiently. Multiplying with 0 or adding with 0 can be an operation that you can bypass or very quickly perform. You don't need to go through the same amount of latency and power as you would with 2 non-zero values. And so you can eliminate some operations during multiplication, addition. However, your hardware needs to take advantage of this sparsity. If you can't take advantage of it, then your performance is not going to be any different than a regular model. So at ESPDAC last year, we proposed this Sonic architecture that really performs hardware-software co-design together with sparse neural network models. And we created this hardware engine designed to accelerate sparse neural networks. So the interesting things here were the actual vector dot product units supported these sparse vector buffers, and we added support for essentially turning off power across microring resonator banks when we encounter sparsity. And that allowed us to create a much more optimized design that had lower power consumption. So here's a look at energy per bit for our sonic architecture, also showing crosslight and other photonic accelerators as well. So you can see that here we get a much lower energy per bit. In fact, the EPB is about or more than 10x less compared to crosslight. So again, this is us moving in the right direction to make these accelerators a little bit more suitable for edge and IoT environments. All right, so now I'm gonna, for a few minutes, just talk about some open problems and future directions that we can explore in this domain. Any questions? I'll maybe pause for a few seconds. All right, so let's continue. So the first open problem that we face today is dealing with these massive models. If you look at in this figure, I've shown not the most latest results, but this is models that are really large. With as we go along towards the middle, we're looking at billions of parameters, and at the end, towards the right and the top, we're looking at models with trillions of parameters in them. So the question here is, how do you support trillions of parameters in an accelerator? Really, this is a challenge for any accelerator. Trying to even run inference with these very, very large models efficiently is a massive challenge. And so today, we don't know what the best ways are to scale up to that level of complexity. The second challenge is supporting efficient training in the optical domain. So up to this point, all the accelerators that I've talked about, in fact, a lot of accelerators today just focus on inference acceleration. Particularly if you look at edge IoT environments, all accelerators are inference accelerators. None of them can really support the very compute intensive and memory intensive operations required during training. And then even other accelerators today, most of them are meant for inference acceleration. So all of the optical domain accelerators that have been proposed today, including the ones from our group, focus primarily on inference acceleration. Training requires today, if you make use of backpropagation and related methods like backpropagation over time, we really need to support this backward pass. And we need to be able to calculate gradients, and all of that is quite challenging. And trying to distribute the parameters efficiently in the backward pass is also not that straightforward to accomplish. So this is an open problem for optical domain acceleration if you want to also accelerate training. The third sort of open area of research and open challenge is supporting sort of scalable platforms for acceleration, in particular 2.5D interposer-based platforms. So we're increasingly adopting these chiplet-based 2.5D platforms today, and our accelerators should be able to also make a dent in terms of being able to support these sort of chiplet-based structures. And so just as an example, at the DATE conference earlier this year, we talked about a 2.5D chiplet platform and accelerating within the photonic or optical domain on that platform. And so again, the components that are used are quite similar. We just make use of these chiplets on an interposer. We can have memory, we can have many other types of components, but we showed how we could actually make use of different types of accelerator engines across chiplets, and also how we could connect these together using an optical substrate. So that's another sort of interesting aspect of what needs to be done in the 2.5D domain. You not only need to accelerate the computations efficiently and move things around within a chiplet, but you need to very efficiently handle data movement across chiplets and any memory components. So at ICCAD last year, we had talked about and we had proposed this recipe photonic interposer network architecture that allows us to make use of optical domain interconnects as part of a sophisticated network that can allow us to transmit at a very high bandwidth data between chiplets. And so we showed that this particular recipe architecture outperformed other architectures. So x-axis shows different applications across the metrics of latency, power, and energy. Y-axis shows just the average delay, average power, and normalized energy. You can see a recipe has the lowest energy, the lowest power, and then in terms of latency, we are not always the best, but we can actually in most cases perform better. And so here's a look at what happens when we take some of our optical domain computation engines and we use this recipe type interconnect to interconnect these engines to create a much larger, more scalable accelerator platform. And I've shown a comparison between a crosslight, and we've created two different variants of crosslight in the 2.5D platforms. One that makes use of an electronic interposer, just metal wires between chiplets, and the other makes use of optical interconnects between interposers, between chiplets. And we're looking at different models on the x-axis, and then the last set of bars is average results, and we're looking at latency on the left and energy per bit on the right. So a couple of trends to notice. So first of all, you will notice that in general, if you just look at latency, your photonic interposer, photonic network-based interposer, actually has lower latency, except for the case of LINET5. So unfortunately, some models, if they're really small, like LINET5, they're really not a good match for very complex platforms, like a chiplet-based platform, which just introduces a lot of inefficiencies. So that's why we don't really do well in these very small models. However, as the model complexity increases, we actually see significant benefits. So we can get a significant improvement in latency, about a 6.6x compared to a monolithic 2D crosslight implementation. And then if we go to now energy per bit, we also notice sort of a similar trend, that there is a bit of a higher energy per bit for a very, very small model like LINET5, but for all other models, our photonically connected photonic computation engine actually has the lowest EPB. We get about a 2.8x on average reduction compared to crosslight when we use this sort of an engine. Also, something to note is these orange bars representing the electronic interposer along with the optical compute engine. You can see that in most cases, using an electronic network between the chiplets increases your EPB and increases latency quite dramatically. And that highlights also the importance of an optical ecosystem where you're doing computation and communication, both of them, in the optical domain. So in summary, these sort of 2.5D platforms are really scalable and allow us to implement large numbers of parameter-based models. And the heterogeneity that these sort of platforms offer, the scalability that these platforms offer, create new opportunities for hardware-software co-design. And so this was really just one of the first works to look into that, but there's a lot of open problems that folks can explore for designing good optical accelerators in the 2.5D type of platform. The next challenge that we face today is data storage. So we're able to compute optically, we can communicate optically, but we have to rely on electronic memory. So could we do something about that? So we started to explore this particular problem, very difficult problem, And some of the early work that has come out of our lab is looking at doing this sort of reads and writes to memory using components like phase change memory cells in sort of the optical domain, or assisted with the optical domain. So we've been exploring different types of PCM materials, phase change material, to try to see which one is the most relevant, so that we could actually use laser pulses to write. In other words, change the phase from amorphous to crystalline, or crystalline to amorphous, efficiently, and also use sort of optical pulses to read. So by changing the refractive index of these materials, we can actually optically read and optically also write these sort of cells. But looking at the cell is one challenge, but creating an architecture is another challenge. So we've also been looking at how do we create interesting memory architectures with these sort of optically controlled storage cells. But again, this is largely unexplored area. So there's a lot of interesting open problems that exist here. There's also a lot of potential to combine silicon photonics or this optics with other emerging technologies. So as just as an example of that, a few years ago, we proposed this BP Lite CNN accelerator, where we actually made use of optical interconnects, but then we connected together resistive RAM compute arrays with these optical interconnects. So there's an interesting possibility to combine other technologies together with silicon photonics. And so we actually showed quite a significant benefit in terms of energy efficiency, both for training and inference. So here we were able to support training as well as inference. All right, so I am at the end of what I have to say about optical computing. So to sort of wrap up, hopefully, you agree with me based on what you've seen that optical computing is an exciting new area. There's a lot of open problems. Our work shows how optical computing has many benefits in terms of performance, energy efficiency, scalability. There are many startups that are emerging that are focusing today on optical computing. So this is a very exciting area to work. If you're a student, there's a lot of career opportunities in these companies. Also, large companies like Intel and HPE, AMD are also all working on optics for communication, and also starting to work on optics for computing. And I actually work with some of these companies. We collaborate with them, and there's a lot of interest and excitement around this area. Of course, at the end of the day, the thing that at least we are very excited about is what if we could enable optical communication, optical computing, and optical storage. If we could do that, we could create some really interesting architecture. So that's sort of the sort of end goal eventually. We are not there yet, but we're slowly getting there. All right, so another thing that I want to mention is that if you are interested to learn a bit more about silicon photonics for machine learning, we published a survey a few years ago that is available on my website. This survey gives a very nice overview of all of the challenges across the different levels of devices, circuits, architectures, and different types of models. And we also go deep into the history of computing in the optical domain. Turns out that optical computing has been around since the 60s. So it's not new, but the older forms of optical computing required large setups that required you to use a big desk and put optical components. And that's not something we can really scalably use. No, today what we're looking at is just these integrated optics accelerators. So these are things that can be fabricated on a chip, and that's a very different scale of acceleration than some of the older work. But this survey paper talks about developments of optical computing and acceleration. So it could be a nice way to understand more about this area. And then lastly, I just want to thank all of the students in my lab, and then also all of the collaborators that I had, without whom all of this work would not be possible. And then also thanks to all of the funding agencies that have provided the funds to support students and to perform this research. So I will stop at this point. If you have any questions, you are welcome to reach out to me. You can email me and I'll be happy to answer any questions that you have. If you're interested in doing graduate studies, or if you just want to do some research in this domain, and if you need any guidance or inputs, I'm happy to talk to you. All right, any questions at this point? Okay, so if not, then I want to thank you for your attention. And again, there's a few books that I have co-authored and co-edited that may be of relevance. All of the details can be found on my website. But thank you again. And I hope this education class was useful. At least it hopefully gave you an introduction to this exciting area. But of course, if you want to do something interesting, there's a lot of work and a lot of papers and a lot of books that you need to read. But I'd be happy to help. So please feel free to reach out. Thank you again, and good luck.